So at this point, you may be stopping and saying, does this shortcut work for complex eigenvalues? But you might not want to wonder that too loud, because you know, if you wonder that, I'm probably going to respond with, well, let's try it. And indeed, I am going to say that right now. Let's try it. Let's see what happens. So does this shortcut work with complex eigenvalues? So let's say we have a system and I want you to solve this. Again, we have another damped harmonic oscillator. Why do I know it's a damped harmonic oscillator? Because I look at our B value right here. Again, we could think of this as a mass of 1, a damping coefficient of 4, and a spring constant of 13. Or again, any multiple of all of those, because you can always multiply everything by 2, multiply everything by 5. We don't know what these values are, but we know their ratios. Okay. So if we were to solve this system, we could start with a guess. Maybe we think that this is what our answer is going to look like. Because we actually do remember that in the complex case, this is actually still what our solutions look like. Just sometimes S is complex. So if we do that, again, we just plug in. What's the second derivative of this particular solution? It's still S squared e to the st. This is still... the first derivative is still s e to the st. Oh, wait a minute. These are exactly the same steps that we did before. We're going to factor in e to the st out just like we did before, and we're going to get a polynomial that needs to equal 0 just like we did before. This is nothing new. And you might notice a relationship between this polynomial and our original differential equation. Huh. I wonder if that's always going to be the case. Who knows? Yeah, it will be. Okay, so you could complete the square, use a quadratic formula. I don't think completing the square gets enough love. Remember, if you take half of this and square it, we have a perfect square. So s squared plus 4s plus 4 needs to equal negative 9, because 13 is 4 plus 9. Let's move the 9 over. S plus 2 squared is negative 9. S plus 2 is equal to square root both sides. We get plus or minus 3i. We'll find that s is negative 2 plus or minus 3i. Isn't that much nicer than the quadratic formula? Who even likes the quadratic formula? Computers do. And a lot of people who don't want to use completing the square, but it's a great method. So, of course, this is a complex number, but that's no problem. This just says we have a solution when y is equal to e to the s, which again was 2 plus or minus 3i times t. That's a solution. Oh, negative 2. Did I write that? I did not. Negative 2 plus or minus 3i. And we know how to translate that. It's with Euler's formula. Remember, Euler's formula says e to the a plus bi is just e to the a times e to the bi. And that second thing is just cosine of b plus I sine of b. So we apply Euler's formula to rewrite this. We get e to the negative 2t times cosine of 3t plus I sine of 3t. No problem. And we remember that if we have a solution, let me rewrite this real quick. If we have a solution to a differential equation, and specifically, we're going to notice that we have a complex solution to a real valued differential equation. An equation only holds true if it's equal. A solution is if the equation is true. Well, if the original thing only has real numbers and we have a complex solution, that means that whenever we take the derivative of something that's complex, this is just a number. It just comes out in front. So each of these individually must satisfy that differential equation, and you can double check. Because just like when we match polynomials, right, if I tell you ax squared plus bx plus c equals 3x squared plus 2x plus 5, Well, the coefficients have to match up. It's the same thing here. If this solves the equation, then each of these are going to be solutions because there is no imaginary part in the equation itself. Right, so these are both solutions. And we remember from section 3.4 that, okay, we have two solutions. We can use the linearity principle to get our general solution. It's just any constant times our first solution plus any other constant times our second solution. We find our general solution to this damped harmonic oscillator. And if we wanted to, we could find what v of t has to be. The velocity, or the derivative, is just going to be the derivative of this. And yeah, we're going to have to use the product rule. So it'll be a little messier. But that's no problem. Okay? So we could find this. But I'm not going to right now, but you could. And that's our answer. So that's one of the nice things about the shortcut is sometimes we don't even have to take more derivatives. We don't have to find the vector valued function. We didn't have to find the eigenvectors at all. Did you notice that? That was always my least favorite part of solving systems with complex eigenvalues. I hated finding the eigenvectors. We didn't have to do that. That saves a lot of time. Is this a 30-minute video? I don't think so, at least not yet. We're getting close to being done. So there's a lot of advantages to using this shortcut method. So let's generalize this method that we're using. So it's this little guessing shortcut. First off, what problems does this work for? This works for problems of the form a times the second derivative plus b times the first derivative plus c times y. Oh, I wrote it down wrong in my notes, but there definitely needs to be a y here. Equals 0. This is constant coefficient, linear, homogeneous, second order differential equation. So if it's not looking like this, we're not using this specific shortcut. All right, what do? First, we guess a solution. Maybe our solution looks like e to the st. And then we plug in. And it's always going to look the same, right? Notice how I said, hey, look at the relationship between these two things. It's always going to work like that. So specifically, what's going to happen when we plug in? We're always going to get that as squared plus bs plus c, equals 0. And that'll be our characteristic polynomial. We'll need to find the roots of this. The roots will tell us a lot about the behavior of this system. And then we can use those roots to find the general solution. And if we wanted, we could find the vector solution as well. So this last step is optional. And again, this will be the scalar solution. So that's what we've introduced in this section. And I said there's two things we're introducing in this section. This shortcut, which we've now fully introduced, as well as some qualitative analysis, which is where we go from here. I do want to take a quick moment before we end this video to say of like some good and some bads here of this shortcut, right? It skips finding the eigenvectors. And that's really nice, especially for complex eigenvalues. So this saves a lot of calculations, which is great. I love that. It skips systems. We didn't have to convert it into a system. We didn't have to find the system. We didn't have to deal with vector valued functions at all. Right? We only had scalar valued functions, which is nice. So these are some really, really nice pros. Unfortunately, there are some cons as well. And this is one that maybe I feel more strongly about than you all, But I feel like when we just follow a step-by-step process, we lose the picture. We lose the big picture. We lose any kind of real conceptual understanding of what we're doing. We get the answer. And this is fundamentally like the mathematical struggle of the ages. Is math just plugging something in and getting an answer? And I would say no, that's not what math is about. And that's a lot of times how math is taught. But real math is understanding how things relate to each other, understanding why we can do what we're doing. And I know there's a place for just getting to an answer quickly, and you all can decide that for yourselves. The more applied you are, the more you just want to get to the answer quickly and let someone else worry about the theory. But maybe you care more about the theory. Maybe you care more about the connections. I actually do care. I'm actually more on the applied side. But I do think it's important to see the connections, or else you just kind of lose an idea of what's going on. So I do think that is pretty unfortunate. And it also has less qualitative analysis power. We're going to do some really cool qualitative analysis. Well, it's not that cool, but it's cool how we can do it later on in the section. And you can't really do that unless you have a system. But we can always convert it to a system. So this is really not that big of a con. So like we can always undo this con by converting our answer, right? If we do this extra step, then that takes care of that last con. That's pretty much it. Oh, it also doesn't generalize great. But this is really kind of the big thing. Any kind of algorithmic focus to solving a math problem is going to maybe lose the big picture in the long run. So watch out for that whenever you're doing this. Try to answer questions like, why am I doing this? Where does this come from? It'll be good for you to kind of remember and not forget things and kind of understand how it fits into the bigger picture. Or you can forget it. It's your prerogative as well. That's it for this video. In the next video, we're going to start classifying different kinds of harmonic oscillators. Yes, and we're going to see chapter 3 come back because we're still in chapter 3. Chapter 3 is about systems. And even though we're talking a lot about second order equations, we're going to use all the powerful things that we learned about qualitative analysis to say something about these harmonic oscillators that we're looking at. It should be good. So you'll find out when you come back. Adios. Bye-bye.